So we're going to start this particular lecture video by kind of rewinding just a little bit to where we were at the end of last class. So at the end of last class, we were talking about the Bohr model of the atom. And in the Bohr model of the atom, we were looking specifically at how the nucleus is surrounded by these different energy levels, and that the electrons exist on those energy levels and have a specific energy as a result. And therefore, light we could describe as having both a particle and a wave-like existence, because if we go back to the photoelectric effect, we could clearly see that light had particle-like properties, energy, that was able to kick out electrons. So one particle of light replacing one particle of electronic charge. And we were able to see that through that, we could go and examine more particle-like sensibilities for light. Now, the focus of today is going to be looking at, well, what does that mean for particles? And so I'm going to show a couple of video clips here from Professor Dave Explains to try to give us a starting point for picking up that particular idea.
Hey guys, it's Professor Dave. Let's talk about quantum mechanics.
He knows a lot about the science stuff. Professor Dave Explains.
So we've seen how the first steps into quantum theory gave us the idea that all energy is not continuous, but quantized, and that light obeys wave-particle duality. The next idea came courtesy of Louis de Broglie, pardon my poor French pronunciation. He reasoned that if waves can behave like particles, then particles must also behave like waves. In his de Broglie relation, he showed that the wavelength of a particle is inversely proportional to its mass. So we must now understand that all matter has a wavelength, from subatomic particles all the way up to your body and even a star. A macroscopic object like a baseball will have a wavelength that is trillions of times smaller than the nucleus of an atom. So we don't need to think of baseballs as waves. Newtonian mechanics work just fine to talk about the motion of objects we can see. But an electron has a wavelength that is very significant compared to its actual size, so we can no longer think of electrons as particles. We must think of them as both a particle and a wave. Wave-particle duality just got extended from light to matter. Erwin Schrodinger wanted a way to describe the wave mechanics of the electron, so he developed quantum mechanics to do just that. And as a result, we can no longer think of an atom as electrons revolving around a nucleus the way planets revolve around a star. We have to think of an electron as a cloud of probability density that represents regions where the electron can be found. Werner Heisenberg soon showed that as a result of quantum mechanics, there are fundamental limitations to what we can know about a particle like an electron, so he formulated his uncertainty principle. The main ramification for chemistry is that the more we know about the location of an electron, the less we know about what it's doing, or its momentum. The more we know about what it's doing, the less we know about its location. This has nothing to do with the limitations of our measuring instruments. It is an inherent quality of the electron. If we could know both its location and momentum with complete certainty, then we could describe it as merely a particle. But it is not a particle. It is both a particle and a wave. This seems to defy common sense. So how can it be true? We have to get used to the fact that common sense
All right, and so the video is stopped there because it actually goes further than what we want to do. So another video clip I have here is just kind of getting into what the Schrodinger equation is and what its ramifications are. And that really is going to be the bulk of our discussion today.
Through the work of Planck and Einstein, we were forced to accept that energy is quantized, and that light exhibits wave-particle duality. Then de Broglie extended this duality to include matter as well, meaning that all matter has a wavelength, from a tiny electron to your whole body to a massive star. However, an object's wavelength is inversely proportional to its mass. So objects bigger than a molecule have a wavelength that is so tiny that it is completely negligible. But an electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be? We can regard an electron in an atom as a standing wave, just like the kind we learned about in classical physics, except that rather than something like a plucked guitar string, an electron is a circular standing wave surrounding the nucleus. If we understand this, it becomes immediately apparent why quantization of energy applies to the electron, because any circular standing wave must have an integer number of wavelengths in order to exist. Given that an increasing number of wavelengths means more energy carried by the wave, we can see the Bohr model for the hydrogen atom begin to emerge as we imagine a standing wave with 1 wavelength, and then 2, and then 3, and so forth. This is the reason that an electron in an atom can only inhabit a discrete set of energy levels. The circular standing wave that represents the electron can only have an integer number of wavelengths. When an electron is struck by a photon of a particular energy, this energy is absorbed, promoting the electron to a higher energy state and increasing the number of wavelengths contained within the standing wave. This is why the electron goes to inhabit a higher energy level, and this is what is fundamentally occurring during electron excitation. Furthermore, it is the constructive interference of these standing waves that explains how orbital overlap results in covalent bonding, so we can enjoy a little more clarity in our understanding of chemistry thanks to modern physics. Once it was realized that electrons exhibit wave behavior, the physics community set out to find a mathematical model that could describe this behavior. Erwin Schrodinger achieved this goal in 1925 when he developed his Schrodinger Equation, which incorporated the de Broglie relation. This is a differential equation which utilizes concepts in mathematics that are beyond the scope of this series, but we can certainly discuss the conceptual implications of the equation. Essentially, just as F equals ma applies to Newtonian systems, the Schrodinger equation applies to quantum systems by describing the system's three-dimensional wave function, represented by the Greek letter psi. In this equation, this term is called the Hamiltonian operator, which is a set of mathematical operations that describes all the interactions that are affecting the state of the system, which can be interpreted as the total energy of a particle. But while the Schrodinger equation can calculate the wave function of a system, it does not specifically reveal what the wave function is. Max Born proposed that we interpret the wave function as a probability amplitude, where the square of the magnitude of the wave function describes the probability of an electron existing in a particular location. Looking back at the double-slit experiment, we understand the diffraction pattern as illustrating this wave of probability. The pattern is not the electron itself. It is the probability that an electron will arrive at each location on the screen. We can't predict where one electron will go, only the probability that it will arrive at a particular location. If many electrons arrive at the screen, it becomes apparent how their distribution obeys the wave.
All right, so there's a lot to unpack in these particular videos, especially in the last part of that last one. So we're going to spend the next several minutes kind of going through what was talked about in these two videos and trying to put some explanation to them and give us some context to ultimately help us to meet our goal for today, which is to talk about electrons in the atom and their quantum numbers. So let's go back to this idea of the de Broglie waves. So Louis de Broglie suggests that matter has wave-like properties in it in the same way that light has particle-like properties. And as was mentioned in the video, those wave-like properties usually don't matter. But when objects are extremely small and have very small masses, then their wavelengths actually do matter. And the way that we can quantify this is using the de Broglie equation. And the de Broglie equation tells us that the relationship here is the wavelength of the matter is equal to Planck's constant. So again, that's the 6.626 times 10 to the negative 34th joule seconds, multiplied by the object's mass in kilograms, and its velocity or speed in meters per second. So heavy objects like you and me, at least relatively heavy compared to the size of an electron, are going to have very, very large masses, relatively slow speeds, and a big number in the negatives when it comes to our wavelengths. Video said like 10 to the negative 34th. That's probably not too far off, 30 seconds, something along those lines. Now, the consequence of these de Broglie waves comes back to the idea of the Bohr model and why quantization exists in the first place. Because if we think about the wave-like properties of an electron, we can see that if it is going in a circle, it has to have a whole number value for its wavelength. It has to be able to complete the circle. And if it doesn't complete the circle, then it goes out of phase with itself like it's seen here. And we lose all ability to monitor and calculate the energy. So the fact that these standing waves are whole and complete gives us a good idea for why this particular phenomenon exists and why the Bohr model does a good job of explaining the energies and why those energies have to exist in the first place. Now, as far as the uncertainty principle goes, I thought the video did a really good job of explaining that we can't know the position and the momentum of an electron at the same time. We can't define what it's doing and where it is at the same time. Now, don't get caught up in all of the math here. We're not going to use this equation. We're just merely illustrating that the greater we know about one thing, the position, where it is, the less we have to know about its momentum, where it's going. And again, going back to the Professor Dave video, that makes sense as well, because if we could define both of those things well, then we'd be talking about something particulate. We'd be talking about something that behaves Newton's laws of motion. And we know that the electron doesn't. So because of these limitations, because they exist at all, Schrodinger and others developed the concept of quantum mechanics. And quantum mechanics give us a mathematical description to give us indications of what this wave-like behavior goes by and looks like. And so we come to the Schrodinger equation, and the end result of the Schrodinger equation, again, don't get caught up in the math here. We're looking at the concept. Notice I didn't even put the equation here on the slide. But the idea here is that this function, the Schrodinger wave equation, gives us the wave function psi, gives us an idea of how the matter wave varies based upon where it is inside of the atom. And it's all well and good, except for it really doesn't help us all that much to just know what that wave equation looks like. We're much better off taking the Born interpretation, and in the Born interpretation, we end up getting what are known as atomic orbitals. So if we take that wave equation and square it, and this is what Max Born did, what we get is an atomic orbital. And that atomic orbital is a 3D probability map for the electron. So that's what he was getting at the end with looking at the double slit comparison. If you haven't had physics yet, you probably don't recognize that particular experiment. But basically the idea is, if I'm looking at an individual electron, the square of the wave function isn't going to really help me all that much, because the square of the wave function, the atomic orbital, gives me a probability, says this is where it is likely that I'm going to see the electron. But an individual electron doesn't behave necessarily according to that probability. It can still go wherever it wants. But if you were to look at thousands upon thousands upon thousands of electrons in that particular situation, what you would see is that they would begin to obey the wave function, and that over time, the probability map would generate itself. And so the net result of the Schrodinger equation and the Born interpretation, the squaring of that wave function, are these atomic orbitals. And again, atomic orbitals give us a 3D probability map for those electrons. And they come in a variety of different shapes. The shapes that they have are largely related to the energies that they have. The important thing to remember about the orbitals, though, is that they give us the most likely locations of the electrons. Again, they don't give us the actual location of the electron itself. That would break the uncertainty principle, and we're certainly not going to be in the business of doing that. So again, orbitals are born out of this Max Born interpretation of the wave function. And the example that your book gives is if you have a perfume bottle and you are spraying that mist at a piece of paper, an individual particle might find its way outside of this spray range, like this one did, or that one. But if you were to spray this bottle dozens upon dozens of times, what you would see is that this circular pattern would emerge, and all of these little dots would start to kind of come together and tell us, okay, this region here is where we're most likely to find it. Then over here, it's a little bit less likely. And then outside of the circle is almost impossible to find it. But again, the key word there being almost impossible. As you can see, there are still some that go outside of the boundary. As you can see, graphically, we can graph the pieces of the Schrodinger equation here. And what this will tell us is where the electrons are in relationship to the distance from the nucleus. And you can see that in this particular case, we have almost all of the electron density being very, very, very close to the nucleus. And as we go to a certain distance out, it really tapers off. So we're about to get into the orbitals themselves, and there are 4 different orbital shapes. The shapes of the orbitals have everything to do with the energies of the electrons inside them. And the size of the orbitals also have to do with those energies, because as we saw, when we go from one energy level to another, we're going to see a change in the wave pattern of that particular electron, and it's going to be higher in energy. And as being higher in energy, the chance of it being further from the nucleus are going to increase. And so the orbitals are going to get bigger as we get bigger in energy. So here is a representation of the s orbital. S orbitals are all spherical. And as you can see, as we go from 1s to 2s to 3s, the numbers here, 1, 2, and 3, represent the energy levels associated with these orbitals. And as you can see, as our energy level increases, so does the size of our orbital. And as our energy level increases, so does the location of our most likely location to find the electrons. So you can see that in the 1s, the kind of most popular distance is right around 100 picometers. In the 2s, there's a bump here at 100 picometers, but this one around 300 is far more noticeable. And over here in the third energy level, yes, we have a bump at 100. We have a bump at about 250 or so. And then we've got this other one about 700. So these spherical orbitals are going to be very different depending upon the energy level that they are in. Now, a couple of really important notes here. There are s orbitals in every energy level. And that is because s orbitals are the simplest and smallest in energy. And so because they are the simplest type of orbital, because they are the smallest orbital in terms of their energy, that's why we see them in every energy level. The next type of orbital is the p orbital. The p orbitals are dumbbell shaped. With p orbitals, you'll notice that for the first time, we are going to see orientation taken into consideration. So the p sub x orbital is aligned on the x-axis. The p sub y is aligned on the y. The p sub z is aligned on the z. But if I put all of them together, what I'll see is that in composite, I have something that is roughly spherical again. Every single energy level, with the exception of the first, has p orbitals in it. And each shell that has p orbitals in it is going to have 3 p orbitals in it because of the 3-dimensionality and the way that those 3 lobes line up. So, important thing to know. P orbitals are very common. They are found in almost every energy level. And for the same reasons, they're relatively simple, they're relatively low in energy. The only one that doesn't have it is the first energy level, and that's because the first energy level is basically too small for it. With the d orbitals, now we see another layer of complication. These are cloverleaf shaped, with the exception of this last one. And we can again see there is an orientation piece here. The dxz, or dxy rather, is between the x-axis and the y-axis. The dxz is between the x and the z. The dyz is between the y and the z. The dx squared and y minus y squared, these are actually on the x and y axes, similar to the dz squared on the z-axis. Just like with the p orbitals, if I push them all together, I would get something relatively spherical shaped. But as you can imagine, these orbitals are higher in energy. And so we don't actually see them until the third energy level. And so where they become much more relevant to us is in the transition metals. And some of transition metal chemistry is very, very dependent on d orbital notation. Now, there is one last kind of orbital. It is the f orbital. Now, f orbitals are much more complicated. You can see that our number of lobes has basically doubled each time. We went from one lobe, one sphere, to the two-lobed dumbbell, to the four-lobed cloverleaf. The f orbital has 8 lobes. And those 8 lobes are arranged very, very oddly. There are 7 different orientations for the f orbitals. As you might expect, f orbitals very complicated and very high energy. They only exist in the 4th energy level and above. And in those, they are among the highest energy. So we'll get to this more when we talk about electron configurations, but the f orbitals are always among the last to actually have electrons put in them because of their high energy. So we now have established the idea of orbitals. Let's go ahead and look at quantum numbers, because the quantum numbers we're going to use to explain and put some description to what these orbitals are, where they are, what they look like, and how many electrons are present. So a quantum number itself, there are 4 of them in total. And what they help to specify is the energy, the shape, and the orientation of the orbitals inside of an atom, as well as the orientation of the electrons in terms of their spin inside of the orbitals. Now, each succeeding quantum number gets more and more specific. So we are going to start with a very general description of electrons and get to very specific by the end. So our general description is going to start with n, the principal quantum number, and it's just going to tell us the energy level. We're then going to move to L, which is going to tell us the sublevel and shape of our orbitals. M sub L is going to tell us the orientation of our orbital. And then finally, M sub S is going to give us a very specific piece of information about the electron inside. So the first 3 quantum numbers all are kind of describing the orbital itself. Where is it? What is its shape? What is its orientation? The last one actually gives us the electron itself. So the principal quantum number n is a positive integer. It's going to describe the relative size and the energy of the orbital or group of orbitals in the atom. So when we think n, we need to think energy level. Again, going back to our wave mechanics, back to the stuff that we were talking about before, we know that this has to be a non-zero integer number because there can only be a positive number, whole number of wavelengths for a given atom. The angular momentum quantum number, on the other hand, given to us by the letter L. Now, just as a word of note, I tend to use the script L when I describe the angular momentum quantum number, and that is mainly because my L's look like ones, and I want to make sure that you can tell the difference. So you notice on the previous slide, I used a script L for that one there and there. It's the same deal. The book does not do that. They expect that you will know the difference. I'm just saying for a stylistic thing, that's what I do so that I don't confuse it with the number one. Now, in terms of value, the angular momentum quantum number can have any value starting at 0 and going up to n-1. But if you look at the key here tells us exactly what that number means. If you have a value of L that is equal to 0, you are talking about an s orbital. If you are talking about a p orbital, you would say that L is equal to 1. If you're talking about a d orbital, you say that L is equal to 2. If you are talking about an f orbital, you would say that L is equal to 3. Now, technically speaking, there are energy levels greater than the fourth energy level, and there are other orbital sublevels that are possible there, but these are going to be the ones that we focus on because they're the only ones that actually have electrons in them in the ground state. L values of 4, 5, and 6, and 7 exist, and their orbital shades G, H, I, J, and so on are largely theoretical. They only exist as excited states for the electrons to go to when they absorb energy. The word that we want to focus on here, though, is the word sublevel. What we mean by sublevel is that the angular momentum quantum number is telling us what group of orbitals inside of that energy level is our electron in. So is it in an s sublevel and therefore in an s orbital? Is it in a p sublevel and therefore in a p orbital? Is it in an f sublevel and therefore in an f orbital? One important note that we should take, and this is going to come in handy in our next lecture, is that if I have values of n and L that are the same, they will have the same energy. So if I'm looking at n equals 2 and L equals 1, by definition, I'm talking about a second energy level p orbital. So we would call that the 2p subshell. In that 2p subshell, there is the p sub x, the p sub y, and the p sub z, 3 orbitals in total. All 3 of those orbitals have the same energy as each other. No sublevel orbital is going to be better than the others in terms of energy. They all are equal in energy. Again, that'll come in handy a little bit farther down the line. Now, for the last 2 quantum numbers, for the magnetic quantum number, we're talking about m sub L. This defines the orientation of the orbital in space. What we are talking about is a range of values going from negative L to positive L. So if L is equal to 1, m sub L would be negative 1, 0, or 1, which you can see there are 3 possible quantum numbers which match up with the 3 possible orbitals that exist. And similarly, if L is equal to 2, then m sub L would be have the possibility of negative 2, negative 1, 0, 1, and 2. And there are 5 possible d orbitals as well. The dxz, the dyz, the dxy, the dx squared minus y squared, and the dz squared. So our definitions of how many orbitals there are and what those orientations are, they come from these quantum numbers. And keep in mind, these quantum numbers come from the Schrodinger equation. So it all is kind of fitting together in one kind of odd puzzle, but it is all the same puzzle. So the key word that I want you to think about with magnetic quantum number is orientation, or more specifically, orbital. So going back, we had energy level, sublevel, and now orbital. The last quantum number, the spin quantum number, keyword here is electron. This quantum number gives us the electron, and it tells us that it can either be positive 1/2 or negative 1/2. One is spin up, the other is spin down. Those are definitions given to us. But what it tells us is that inside of that orbital, there are two possible electrons, the spin up electron and the spin down electron, which means any orbital has 2 electrons in it, or has the potential at least for 2 electrons in it. And the spin quantum number helps us to tell which one it is. So again, if we go and we look at this as kind of like a funnel, at the top of the funnel, our energy level, when we define an energy level, we take the possibility of every electron in the atom down to a subset of those atoms, or of those electrons. By the time we define the angular momentum quantum number, we've got it down to a potential of, 14 or 12 or 10 or 6 or 2 electrons. The magnetic quantum number gets it down to 2 electrons that are possible, and then the spin quantum number tells us the one that it has to be that we're describing. And this leads us to the Pauli exclusion principle, which kind of piggybacks off of that and says it is impossible for 2 electrons in an atom to have the same number, the same set of quantum numbers. They may have the first 3 quantum numbers the same. They might exist in the same orbital, but I'm going to be able to tell one apart from the other based upon its spin. So here's a look at kind of all of that in total here. So in the first energy level, I have an allowed value of L for 0, which corresponds to the S sublevel. That means that the only allowed value of M sub L is 1. So I have 1 subshell and 1 shell. I know that if I multiply that by 2, it would tell me that there are 2 electrons in the energy level. In the second energy level, I have the L sublevel of S and P. Inside of the S, obviously I have the 1 orbital. Inside of the P, I've got the 3. So there are a total of 4 orbitals in the entire energy level. I can multiply that by 2. That means that there are 8 electrons allowed in the second energy level. I do the same thing. Third energy level, I have S, P, and D available. That means that there are 9 orbitals in total. So 18 electrons can fit in that third energy level. And then finally, the fourth energy level, I have S, P, D, and F available, which gives me a total of 32 electrons around. All right, so let's do some example problems. So First, what are the names of all of the subshells in the n equals 4 shell? And then how many orbitals are in those sublevels? So to answer part A, I would need to go, okay, well, if n is equal to 4, my possible values of L would be 0, 1, 2, and 3. Because remember, we start at 0 and we can go all the way until n minus 1. N minus 1 would be 3. Well, if I pair those up, 4, 0 would be the 4s. 4, 1 would be the 4p. 4, 2 would be the 4d. And 4, 3 would be the 4f. That would be the names of the 4 subshells: 4s, 4p, 4d, and 4f. Now, if I expand upon that, and this is what part B is going to do, let's look at the possibilities if n is equal to 4 and L is equal to 0, then M sub L must also be 0 since it is bound by L and negative L. In this case, 0 and negative 0, there's the same thing. So there would only be one possible orbital in that subshell. For n equals 4, L equals 1, M sub L can equal negative 1, 0, or positive 1. So there would be a total of 3 orbitals in that sublevel. For n equals 4, L equals 2, M sub L could be negative 2, negative 1, 0, 1, or 2. So a total of 5 orbitals in that. And then finally, for n equals 4, L equals 3, M sub L could be negative 3, negative 2, negative 1, 0, 1, 2, and 3, which would be a total of 7. If I add all of those together, 1 plus 3 plus 5 plus 7, I would get a total of 16 orbitals. And since we know that each one of those orbitals can carry 2 electrons, that means that there are 32 electrons that can fit in that n equals 4 shell, the 4th energy level. Now, this particular question, I am going to, this is going to be in your assignment for today. I'm going to give you a little bit of insight on it to kind of help get you started. What you need to be able to do is you need to be able to look at this and evaluate in terms of your rules. So, for example, based on your rules, you know that if n equals 1, L has to equal 0. So that part's okay. But if L equals 0, M sub L has to equal 0 also, which this doesn't. So letter A cannot be a valid set. But letter B, n equals 3, yeah, that works. That's the 3rd energy level. L equal 2, that's a d orbital. So yes, that works. M sub L of negative 2, yeah, you can do that. M sub S of positive 1/2, yeah, that works too. So this would be a valid set. What you need to do is do that for all 5 of them and choose the ones that are valid and submit the answer. And after you do that, you'll want to make sure that you also do this confidence meter question in the assignment as well, so that you can get full credit for today's experience. So that is all for today's video. Please do check in with the assignment. It's assignment 3-3 here. And in it, you will see that there are points associated with everything, along with these questions that we talk about and this muddiest point. And when you finish with this, do bear in mind also that you have a homework assignment inside of Smart Work to do as well to help give you some extra practice. But that is all for the day. I will see you next time in class. Have a good day.